Hi everybody, welcome back to Chem 161. Is that where I'm at now? It's been a long day. What do we got on the agenda? Oh, I didn't write anything about the quiz for chapter 3 on there, but you know that that's been assigned, so I'll put that up for Wednesday's lecture if I remember. And there's a last call out for lab number 4. Make sure to get that in by the deadline tonight. That assignment does close. Where are we? We're in chapter 4. It feels so weird to be in chapter 4 after so long in chapter 3. I don't even know. What even is chapter 4? What is any of this, really? Chapter 4 is about bonding, it turns out. And we talked about electronegativity, which is going to be one of the more important topics in helping us discern what type of bonding we're looking at. So yesterday I gave you this table. Had a bunch of numbers on it. Most of the big numbers were in the top right. Most of the little numbers were in the bottom left. We talked about why that was due to Z effective and because of Z effective electron affinity and ionization energy. That's how we got those numbers. This guy did all that work for us. Then he went crazy, much like I'm doing right now. Because pandemic, right? We're all Linus Pauling in his later years. All right. So let's actually apply electronegativity. So we're going to refer back to those numbers. So what I'm going to do is I'm going to go back to this slide and I'm going to go print screen. And then we're going to put this in the PowerPoint. There we go. So now we have it handy here. So we can just refer to this later. Did I put it on a new layer? Oh, I'm going to sneeze. Hold on. Sorry, I got to hit mute before I sneeze because I sneeze real loud. Okay, so that's now there. We're going to use this a whole bunch. So let's make a new layer. And we'll draw on that. All right. So how do you determine what type of bond you're looking at? Your text gives a reference, and I sort of disagree with one small part of this, which I'm going to edit so that you don't spend all of organic chemistry going insane. All right, so there are 3 categories that we're going to look at. We're going to look at pure covalent, polar covalent, and ionic. And we've categorized the difference between electronegativity into 3 ranges here. I'm going to modify where it says 0 to be essentially 0. And I'm going to scribble out on this chart. We're going to get rid of this less than and say 0.4 or less. And the reason for that is because a very common bond has a difference of electronegativity of this. And if you call that polar covalent, every single organic chemist will slap you. Because the whole point of CH bonds is that they're assumed to be nonpolar. And more or less they are. So what that means is that this number down here becomes this. It becomes a 5. So really, really important that we categorize CH as nonpolar, or else all of organic chemistry falls apart. Okay, so make that change to your notes. Just make sure that you are treating 0.4 as something that is considered to be pure covalent, because for our purposes, it will be. And in fact, for almost everybody's purposes. I just want to say that the book is just wrong by doing that. All right. Something that is pure covalent will have electrons being shared right in the middle, more or less. Something that's polar covalent has the electrons shifted significantly towards the more electronegative atom. That's going to be for the electronegativity range between 0.5 and about 1.8. I say about 1.8 because it kind of breaks down at that extreme. Anything that's ionic is going to have an electronegativity difference greater than 1.8. Another thing that we're going to consider is that whether there is a metal present or not. And for this class, if a metal is present, we're going to treat the bond as ionic. Although you do get some very weird and or interesting chemistry when you put transition metals together with elements that aren't super electronegative. So, for instance, you can make carbon bonds to transition metals, and you end up in the polar region, because carbon is like 2.5, but if you bonded that to, say, like iron, the difference is only 0.7, and you actually get a covalent bond. So the overall, is a metal involved, oh, it's ionic, will be okay enough for our purposes, but later on in chemistry, we're going to discover that, like, even that is a gradient too. And that these rules, these number rules, aren't super great approximations, because this is saying that, oh, well, this, which is rust, I just looked at the chart, and this is the number you get, which we would say, is that polar covalent? No, it's not. It's ionic. So use these as a guideline and not like the absolute end-all be-all. Okay. And again, my slides are written with regards to the textbook, even though I believe the textbook is wrong. So I'm going to modify my numbers here. And then we'll modify this one here too. The upper number are not really, I don't really care about that so much, because you mostly just end up with ionic, if a metal is involved, in most cases anyway. So these are labels that we are going to assign to bond types. And more importantly, using this delta En is going to tell us a little bit more information when we start drawing polarity vectors later on. And that's where this slide is going to go. So how do we illustrate this graphically? So first of all, let's write down the electronegativity of each of these atoms. So hydrogen, according to our chart, is 2.1, and fluorine is 4.0. Now, that is a very stark difference. The difference is 1.9, which we would categorize as ionic according to those rules. Not great, because HF is actually mostly covalent. It's kind of skirting right the fine line between ionic and covalent. But let's assume that it's covalent, it's polar covalent. What do we draw to represent this symbolically? So there's two things that we can do. The first is to draw these delta symbols that I showed you the other day. Delta plus is written next to the less electronegative atom, the more electropositive atom, you could say. And then delta minus is written next to the more electronegative atom. So symbolically, what that would be is I would draw like a little circle where it represents my molecule, and I would do something like this to it to show one side of the molecule is positive and the other side is negative, but not enough that it's an entire electron moved over there. The second thing that you can do, and I'm going to have to clear just this bottom part down here, is you can draw an arrow. And the arrow is going to have a cross slash through it on the side that's more positive, so it looks like you have a plus on that side. And then you just point the arrow towards the negative end of the bond. Now, specifically, we use these delta plus and delta minuses for an entire molecule. So like the overall molecule, like I showed with the blob, you'd put the delta plus and the delta minus on whatever side of the blob has those properties. The arrows are usually used for bonds, but you can use either one for either application. So we're going to look at water, and we're going to draw these polarity vectors for each of the bonds in water, and then we're going to do an overall polarity. And then we'll do that with other molecules too. Now, in order to do that, we're going to have to explore their geometry. So we're going to have to do an entire discussion about geometry first before we can start really doing this. Because what happens if I have something that's polar in this direction, but it's also polar in this direction based on what's bonded there? Well, it turns out these dipoles would cancel. Whereas if I have something like this and something like that, the overall effect is like this. So the spatial orientation of molecules is going to be super important. So we're going to spend a lot of our discussion in Chapter 4 just describing geometry. And that's where we're going to get to eventually. So let's start by just categorizing these bonds based on our descriptions of pure covalent, polar covalent, and ionic. So let's go over here. And let me zoom this in so that we have it available. There we go. That's big enough. And then give me a little more space to write with. Okay. So if I'm going to look at NaCl here, so sodium, I can't even read the damn thing on my screen, is 0.9. And then chlorine is 3.0. So the difference in delta, or the difference in electronegativity would be 2.1. So we would call this one ionic. Now for this next one, for bromine and iodine, I think that says 2.8. It's really small on my screen. This one's 2.5. So this difference would be really small. This is essentially pure covalent. And then for boron and nitrogen, so this is 3.0. That one I know. This one is, I think that says 2.0. It's kind of cut off. Oh, yeah, I'm sorry. Yeah, it totally is. There you go. Sorry about that. I gave myself enough space and then I went and didn't write in that space. I apologize for that. So there you go. So that's our designation. That's how we do this. I'll give you a second to write that down since it got chopped off. Excuse me. Bad time to gulp of water there. Okay. I guess I could just clear what I wrote. All right. Now what I want you to do is apply the same thing. But then what I want you to do is apply either polarity notation. So you can use either delta plus or minus, or use the arrow notation. And then draw that along the bond. So when I say along the bond, I mean something like this, as an example. Now, obviously, that's a bad one to put that on. That one's obviously nonpolar. But if something is nonpolar, don't draw any notation at all, because there's no polarity at all. For something that is polar covalent or ionic, use either notation that you want to. I'll show you why we don't really want to do that for ionic in just a second, and you probably already know what you should do instead. But for the purposes of this exercise, go ahead and you apply that notation to all the molecules that it applies to. So I'll give you a minute or two to do that. I'll see you in a second. I realize that this would be a lot easier if I did this. So you don't have to keep going back and forth through the video. So there's the electronegativity chart. I'll give you a few minutes to do that. All right, one more minute. We'll go over the answers. All right, let me get back to here. I'm going to try to write only in the space that I have allocated myself. All right, so if we look at the electronegativity of each atom, we'll get this. So I'm going to go through and just write in all the hydrogen here. Chlorine's 3, right? Yeah, 3. And then oxygen's 3.5. That one I know. I have no idea what lithium is. 1.0, okay. All right, so those are our electronegativity values. Let's look at our delta electronegativities here. So this is just 0, 0.9, 2, and 1.4. So if I was going to classify these, I would consider this to be pure covalent. 0.9 is polar covalent. Excuse me. 1.4 is polar covalent. And 2 is ionic. Now, just as a heads up, in other texts, or in other contexts, I should say, the words that people are going to use are just covalent, polar, and ionic. So you're going to see those words thrown around. If I say something is polar, that's what it means. If I say something is covalent, then there's essentially no sharing of electrons there. Okay, so now let's draw appropriate symbology. Let's get a different color out for that. I mean, if something is pure covalent, I don't need to draw an arrow in either direction, especially when it's 0. So that one's just good as it is. Polar covalent, let's draw it towards the more negative side. You could also have done that. We'll do the same thing here. This one's going to point this way. You could also do that. And then for ionic, you could do something like this, but it would be more appropriate for an ionic compound. I mean, it's ionic. Just draw the charges, yeah? So we got positive and negative. And in fact, in an ionic compound, we would not even write a line to represent that bond. Hey, look who drew outside of the visible area again. It's me. There you go. Sorry about that. Drawing off the page. There you go. So that's what we are going to be doing in terms of symbology for our bonding. We're not really going to do much more bonding today because we're going to be talking about Lewis structures and nomenclature, which is the next section. But we'll get to bonding next week for sure. Actually, we might do some bonding today. It's hard to say. Okay. What happens if you have polyatomic ions? For example, if I had this molecule or compound, and I wanted to figure out what type of bonding was in there. Well, we've already discussed that something with ammonium in it has an ionic component to it. But if I were to look at NH4, what I actually see is that the bonds in NH4 are something like this. And if I compare the electronegativity of these elements, what I find is that they're just polar covalent. So N is 3.0 and hydrogen is 2.1. So each of these bonds in ammonium is polar covalent, but there's also an ionic bond. So it is possible for you to have multiple types of bonds present in a molecule, particularly if you have polyatomic compounds. Okay, so be mindful that this is not a binary sort of thing, but is instead considered on a bond-by-bond basis. Oh, look at that. I chose the example that I was going to do. So later on when we revisit this, when we start exploring compounds in more detail, just be mindful that anything that has a charge on it has to be ionic. Oops, that's the wrong end of the pen. However, within a polyatomic ion, there will always be covalent bonds. And we're going to be illustrating those in more detail later on. All right. Who knows how to name things? I hope you remember, because we're going to be naming things in this section. We're going to review from 140 all the nomenclature about naming things. This was unit, I want to say, 11 in 140. And we're going to do it in one section here. So let's talk about nomenclature. Here are the kinds of compounds that we're going to name. The term binary is used when there are only two elements in a substance, and so we're going to have binary ionic and binary covalent compounds. And then we have polyatomic ionic compounds, which you need to know your polyatomic ions for. And then finally we have acids. So we're going to go over all these rules pretty quickly because you've done this in 140. I don't need to spend too much time on it. So how do you name an ionic compound? It's very simple. There are two boxes here. You are going to drop the name straight into the box and make the modifications as shown. So naming a metal is easy. You just drop its name right in the box. Sodium, aluminum, potassium, lithium, whatever. However, there is a caveat if the metal is a transition metal. So if your element is in group 1A, 2A, or aluminum, the name that you are going to apply is just its name. You don't put a charge, you don't put Roman numerals, you don't do anything like that. If the metal is any other element, then you need to indicate its charge in Roman numerals. So the 2 right here on this Fe2+ is the 2 right here in Roman numerals. Same with this 4+ on platinum. Now, there are some exceptions to these rules that some texts want you to know are constant. And I don't know if I actually put those on here. I don't. Okay. But if we go to the periodic table, which I still have here, you might see indicated this staircase, which I call the stairway to silver because you're going down the stairs and you end up at silver. For these ions, oh, I lost my thing there. There we go. Elements in this staircase in these columns tend to always be these charges. So for instance, silver is always +1 in every compound we see. I can think of very few examples of silver being anything other than +1. And you will probably never encounter them. So should I write silver 1 in parentheses? For this class, yeah, just do that. It's simpler to just not worry about it that way. Do I have to write zinc or cadmium with a 2 in Roman numerals? Yeah, just do that. Aluminum is really the only one where you don't have to write +3. Gallium, just write gallium 3 and it's fine. People will understand what you're trying to do. Those are just less common. I think of these elements that are in here, probably the ones that I'm going to circle are the ones that are the most reliable. Cadmium's pretty reliable too. But those 3 are by far the most common, we'll say. So for our purposes, again, though, only aluminum needs to be the one of these that you don't put a Roman numeral. Put a Roman numeral for everything else and you'll be fine. That's how you name the metal. How do you name the nonmetal? Well, the nonmetals on the periodic table end in whatever they end in. So, like, nitrogen would end in a gin, oxygen would end in gin, etc. What we're going to do is we're going to take those nonmetal names and we're going to remove part of it and then add "ide" to the end. So I'm going to write down the stems right here for the elements that we care about. So there's fluorine, which I'm going to go like that. We're going to get rid of the ene. And then chlorine, we're going to get rid of the ene on all of these. Bromine and iodine. And then we've got oxygen. We're going to just go ox like that. Sulfur will be sulf. And then selenium will be selen. And then nitrogen and phosphorus will be nitr and phosp. And that's pretty much it. There's not one for carbon because carbide is actually a different compound. It's not carbon with a -4 charge on it. So these are our stems. And I forget if there's a table that has these in your textbook. In case there's not, because if there was, I feel like I would have put it on the slide. Here are all the stems that you are going to encounter in this class. So pause the video if you need to write those down because they're going away now. Boop, there they go. Where those hyphens were, you're going to put "ide" at the end. And that'll be the name of the anion. Now, it's very important that you realize that the "ide" implies that there is an ion, and that you don't just start calling everything "ide," because "ide" is only for ions, which means that if you see something like this, these represent two different things, unlike with metals, where the metal is pretty much just named, and then you have to interpret what the identity of it is out of the context. So, for example, chlorine is just Cl by itself, but chloride has the little minus charge on there, and so that's what that indicates. Note that it's always "ide" for the common ion that forms, so sulfide would be S2 minus and not S minus, or any other charge of sulfur. So now we can just go through the examples. What would you call KBr based on what we've talked about? So type it in the chat. We'll reveal the answer. And then I'll give you the examples, and then we'll move on to the next naming section. There you go. Very good. Potassium bromide. So name the metal. It's potassium. Name the nonmetal with "ide." It's bromine. Get rid of that "ene" and make it "ide." And so you can do this more than one at a time. I'm just going to put this example on the board here because whenever you have more than one, the rules don't change. We do not care about extra numbers, so you just say what it is based on the rules. Name the metal, name the nonmetal. All right, we'll put a bunch of them on the screen. I'll just skip over these examples because you could do these. This is 161. I expect that you know how to do these. So I'm going to give you 3 minutes to name all of these compounds at the top and then write the formula of the ones at the bottom. There is a second page of these, so I'll give you a few minutes to do this first page, then we'll go on to the second page once we got all the answers. Okay, so go ahead and get started on that. Good, now work backwards and do names into formulas, because we got to be able to go in both directions. All right, one more minute, we'll go over the answers. All right, so that's the wrong pen. All right, so we got lithium here, and then oxygen becomes oxide. And we got beryllium, and then chlorine becomes chloride. We got aluminum oxide, because we just did that one. And then potassium. Don't know how to spell potassium. Iodide. There you go. All right, and then down here, we got to just turn these into ions. Now, we know what ions form for each of these things because we wrote out all the electron configurations for them. So, making compounds out of them shouldn't be too hard if we can just get to this step. So I'm going to write out all the ions here. And now I can start putting them together. So strontium and bromide. I need a second one of these to get the charges to cancel. So that would be its formula. For rubidium nitride, here's rubidium. Here's nitride. Need more rubidium here. That will cancel these out. 3 plus, 3 minus. Those are good. There you go. And then I ran out of space. We'll work up here, I guess. And then for the last one, for magnesium 2 plus and iodine minus, we just need another iodine. There you go. So those are the answers. You had them right. Good work. Let's now do the next slide. Do the same thing. Give me the name of the formula that is formed from these ionic pairs up at the top here. And then at the bottom, write out all the ions that make these molecules, and then give me the formula of the ionic compound too. Okay, so I'll give you 3 more minutes to do that. We'll go over those answers, then we're due for a break. See you in a bit. All right, 1 or 2 more minutes and we'll go over the answers here. All right, let's go over the answers here. So same thing as before. We can put all these together to get this. Then we got to give it a name. So here's the name of the cation. So that's cobalt 3, and then bromide. Be really careful when you are naming these things in Canvas. There is no space between the name of the metal and the Roman numerals parentheses. Canvas will mark that wrong when it asks you type in this name, and I believe it says on those problems don't enter excess spaces or excess parentheses. Just enter one set of parentheses with the Roman numerals in them. So just be very careful about that. So there's our TiO2, there's our formula. This is titanium 4. And then oxide. And then I'm going to run out of room, but we can see that these two both go together to just give us that. And then the name of that would be chromium 2 sulfide. For your Roman numerals, make sure you're typing them in capital letters. Lowercase will get marked wrong too, so just be careful. We don't say di or tri because the formula will always be the same with given ions. So chromium 2 implies that we will always have a +2 charge, and the ion paired with it will always lead us to one formula. We don't use di or tri because it's sort of redundant. Later on, when we do covalent compounds, we'll put the di and tri prefixes in there because it will matter. So like carbon with 1 oxygen versus carbon with 2 oxygens. There aren't charges in covalent compounds, so we can't use Roman numerals. We have to have something else to distinguish them. So no di or tri or numeric prefixes in ionic compounds. So I'm going to just go down the list here and write in all of our ions here. So barium, 2 plus, O2 minus. We'll put this one down here. So now I can make the formulas. 1 gold plus and 1 Cl minus makes this. I think we've done that compound like 75 times. These two cancel each other out, so we'll just do that. And then I need 4 of the fluorides with my 4 plus platinum to get this. That should all be review. So you should be able to do those compounds. No problem at all. When we come back from the break, we are going to continue. We'll do polyatomic ion compounds, and then we'll do covalent compounds, and we'll do acids, and that'll probably be all we can fit in today. So, yeah, okay. So let's go to the break time timer. And I'll hit start on the clock, take a 10-minute break, play some more Final Fantasy music, and we'll see you after the break. So I've been playing the Final Fantasy 1 through 14 world map themes this week. And I played hundreds of hours of Final Fantasy 14. I don't recognize this song at all, which is kind of funny. I did turn off the music for most of that game, because when you play a game for that long, the music starts to get samey. Okay, so let's go over here. And let's get back to it, ready for more. So, try and finish up the naming for today. Let me try to say that again. We're going to try and finish up naming today. And if we can get to Lewis structures, that's great. Otherwise, that'll be tomorrow. So, polyatomic ions, same as ionic compounds. All you do is drop the name of the polyatomic ion into whatever box you have. There's only one positively charged polyatomic ion, so you're only ever going to ever drop ammonium into the metal box if it's present. Otherwise, all the others are going to go into this box right here. So, whoops, all others. So if you see a polyatomic ion in your compound, instead of naming the metal or naming the non-metal with "ide," you don't modify the name at all. You just drop its name directly in the box. And the polyatomic ions were listed at the start of Unit 6, it looks like, according to these slides. I believe that that's right. So if you have your slides or even the video from Unit 6, go to the first video for Unit 6 and you can look up all of those. Those are all in there. You will need them to do the quiz for Unit 4. If you haven't memorized them, and it's an online class, I'm not going to force you to memorize them. If you work with these enough in an in-person class, I would make you memorize them. But on here, you can use whatever resources you want. It's fine. So this does require you to look up what particular polyatomic ions these are, and also know what their charge is. So you're going to have to be very careful about looking them up and making sure that you get the correct one, because some of them are similar, so be careful. So this would be potassium permanganate, because that's the permanganate ion right there. This right here, I'll actually write above it here. So this is either hydrogen sulfite, which is this, or bisulfite. And so that would be sodium, and then the name of the polyatomic ion. So you could say sodium bisulfite or sodium hydrogen sulfite. Either one is acceptable. And so, with that in mind, you are going to have to go look these up. Got to go find them. If you don't know them off the top of your head, or you didn't memorize them from 140 or whatever. So what I want you to do is give me names for these compounds based on the polyatomic ions that you see. They follow the ionic rules, so we're going to apply what we did just now to this. And then down at the bottom, write as best you can the formula for the compound that is shown into the chat. Okay? Be careful. Sometimes I try and mix in polyatomic ions with regular ions. I don't think that I've done that in this case. I don't see any anyway. But don't accidentally look at this and go, oh, I see this. This is probably this. Because it's totally not. Nitrite is something very different. So be careful when solving these problems, okay? We'll go over the answers in about 3 minutes. All right, 1 or 2 more minutes. We'll go over the answers. All right. So this really is just an exercise of finding the names of these. So I'm going to write down the answers here. So we got ammonium sulfate. I don't know how to spell. Sulfate. There we go. This right here is chlorate, so this would be potassium chlorate. Then we got barium carbonate. And then this right here is dichromate, so this would be lithium dichromate. And then going in the other direction, we need to be able to identify what the polyatomic ions are. So sodium is easy. Hydrogen carbonate is that. So this would be our formula. Then we've got ammonium, NH4 plus. Nitrite is NO2 minus. We just put the charges together so that they cancel out. We got potassium and then phosphate. I need 3 of these to balance out this 3 minus, so we would get that. Just like you've been doing all along for ionic compounds. Should be pretty straightforward. I have more of these on the next slide. I'm going to just write down the answers so we can move on to the next topic here. But you can look these up and do them on your own time. Just hit pause before I started writing the answers down. So those are the answers to those. And those are just using some extra examples, but also with transition metals, because remember that things like this, nickel 2 is that, molybdenum 6 would be that, and then the rest are pretty self-explanatory. All right. And then I have more slides of like, how do you write polyatomic ions? Well, you just put parentheses where you need to. So, for example, this is chlorate. If I have 2 of them, I got to put parentheses here and here. If I don't, I end up with this going on. Obviously, there's not 32 oxygens bonded to this poor chlorine. So make sure that you are using parentheses when necessary to get the correct answer. Polyatomic ions do not split apart. So make sure that if you have 2 of something, you aren't putting a 2 after everything. Instead, put parentheses around it and put the 2 there. All right. And then more examples to just put those together. So I'm going to leave those for you to do. All right, let's talk about covalent compounds. Covalent compounds are where we start to get the numeric prefixes. So what these boxes indicate are the numeric prefix that indicates how many of those are in here. But other than that, we just follow the same rule. Name the first element, name the second element with "ide." The first element is going to be whichever element has the lowest electronegativity. It's the element that's the most positive like. And then the second element will be the one that has the higher electronegativity, the one that's the most negative. So if you're ever given, like, what compound can you make out of sulfur and carbon? Carbon would go first because its electronegativity is lower, and then sulfur would go after. That matters because the second element has "ide" tacked on the end as if it were an anion. It's not an anion, but we name it as if it were one. And then again, the number box is for your numeric prefixes. But remember, we only use numeric prefixes for covalent compounds. So don't do this rule for ionic. These rules are different. Be very careful you don't mix them up. If you start putting like sodium, disodium oxide or something like that, Canvas is just going to have a field day marking all your answers wrong. So be very careful. You only apply numeric prefixes for covalent compounds, never ionic. Online, you might see some common names that include prefixes. Those are not written correctly following IUPAC nomenclature. So be mindful of that the internet may give you the wrong answer. So follow the rules that we've established in these slides. So let's do some examples for these. Here are the numeric prefixes. If you have one of something, you would write mono. If you have two of something, you would write di, and so on and so forth. There's a little note here. This is sometimes omitted. If the first element only has one, you don't write mono. So for example, if I had CO2 here, we would not say monocarbon dioxide. We would just say carbon dioxide. Likewise, if I had CO, I would still say carbon monoxide. And there's the mono right there. You'll notice that it seems like it's missing an O. And that's because if you end up with a pair of vowels like this, AO or IO, specifically these two combinations, you get rid of the first letter in that pairing. This specifically comes up with oxygen. And the only reason that this is done is apparently it just sounds better. So some examples of that are listed below here. Instead of pentaoxide, we have just pentoxide. And then for monoxide, there isn't a double O there. This last little note just says never use Roman numerals in covalent compounds. Roman numerals are only for charges. And remember that covalent compounds are not ionic. They have shared electrons. So there are no charges. So if there's a place to mess up in naming molecular compounds, it would be putting in Roman numerals on accident. And if there's a place to mess up on ionic compounds, it would be trying to apply numeric prefixes. Those are unique for each thing. So Roman numerals are for ionic. Numeric prefixes that we see here are for covalent or molecular. All right, so let's do some examples here. Well, what I call this. So I have two nitrogens. So I would put the numeric prefix for 2 in front of that. And then I have 5 oxygens. Oxygen is the second element in the compound, so I would name it as an ide. And then I'd put the prefix in front of it for 5. So easy as that. Naming these is pretty straightforward. So what would I call this? Well, there's one sulfur. And then there's 2 oxygens, which we'll name oxide, so we'll just go dioxide. There you go. Lastly, what is this? You might say, oh, it's water, but what's the actual chemical name for this? Well, this is the element it listed first, and there's 2 of them. This is the element listed second, and there's only 1. Why is it important to have a systematic scheme of naming? Well, this is the proper term for water in terms of chemistry. So, as a chemist, calling something dihydrogen monoxide is useful in a setting where we want to have all of our elements and compounds named in the same way. However, this can be used against you. And this next slide will be appropriate for my I am slowly going insane with this pandemic and all the news that's going on today slide. How do people take knowledge and use it against you? Well, they provide it out of context and try and twist it so that it sounds scarier than it is. So there's a, we'll call it fun, but it's also kind of frustrating story about dihydrogen monoxide, or as some websites call it, DHMO, because that sounds scarier. And they list all of these terrible, terrible things that dihydrogen monoxide can do. So, for example, dihydrogen monoxide, major component of acid rain. That sounds pretty awful, right? I mean, acid rain is bad. And most of acid rain is dihydrogen monoxide, right? Did you know that it's a greenhouse gas? It holds heat more effectively than CO2. We're not even worried about dihydrogen monoxide out there. If you come into contact with it, it can cause severe burns, and if you breathe it, you will die. These are all terrible things that dihydrogen monoxide does. Did you know it erodes natural landscape? Yeah. Grand Canyon, dihydrogen monoxide. What else can it do? It can corrode metal. It facilitates rust. It can lead to electrical failure. Your automobile brakes can fail because of dihydrogen monoxide. Every single person who's had cancer has this in their body. Like, it's so awful. And yet, despite all of these things, here are other places dihydrogen monoxide is used. And do we care? No, we use it in industry as a coolant. We use it in nuclear power. We use it to make styrofoam. We use it as a fire retardant. We use it in cool animal research. We use it in pesticide. Even if you wash your produce, it's still contaminated by dihydrogen monoxide. It's used in junk food. All of these places use dihydrogen monoxide. Should we be concerned? No, it's fucking water. So be careful. People will use chemically sounding names to try and scare you and manipulate you, because all of these sound really bad. But yeah, they're water. Yeah, if you heat water up to near boiling and then take a bath in it, it'll burn you. If you dunk your head underwater and take a deep breath, lights out, right? Like, no, those are bad things. And we know that. But these facts can be manipulated against you if you aren't aware that these are just the rules for nomenclature that scientists use. So don't be afraid of chemically sounding names. In fact, there's a large push from people who aren't educated in chemistry specifically that they hear the word chemical and they go, oh my goodness, I don't want any chemicals in I don't want my children to be exposed to chemicals. And to that I say, well, I hope you enjoy starving, because everything is a chemical, right? Like, a chemical is just a molecule that we can ascribe a formula to. So be careful about verbiage and nomenclature. And that's the whole point of why I'm giving you all these names, because sodium chloride sounds a lot scarier than table salt. So just be mindful of that. All right, here's some stuff that I want you to name, and then also write the formula to. I think that this is a lot easier to do. So within 2 or 3 minutes, you should be able to do this, and we'll go over the answers, and then we'll do acids, and then I think we'll be done. So see you in a bit for that. All right, one more minute. We'll go over the answers. Type anything you got in the chat. All right, let's go over the answers here. That's the wrong pen. There we go. So I got nitrogen, but there's two of them, so I'll write dinitrogen. And then I have one oxygen, so that's monoxide. Down here I have two chlorine. I have dichlorine. And then three oxygens is trioxide. SF6, we got one sulfur. Don't put mono on the first element. We'll just put sulfur. And then 6 is hexa fluoride. Wait, how can you bond 6 things to a single atom? I thought 4 was the limit. We'll talk about that tomorrow. Maybe tomorrow, maybe Monday. And then finally for P4O10, we have tetraphosphorus decoxide. And then write the formula for these compounds. Diboron is B2. Trioxide is O3. Carbon is just carbon. Disulfide is S2. And then oxygen difluoride. Pretty straightforward for doing covalent compounds. The trick is not to get the rules mixed up with other rules we've already learned. Excuse me. But this is all review from Chem 140 anyway, so that's why we're going through it so quickly. Any questions, let me know in the chat. Let's do acids. How much time do we have for acids? I got about 10 minutes, so we could do that in 10 minutes. All right. What is an acid? An acid is hydrogen paired with some other thing that dissociates so that H plus is one of the things that comes off it. So like HCl, hydrochloric acid, would be this, and it would split into H plus and Cl minus. If I have multiple of them, and I dissociate it completely, I would get something like that. There's always going to be enough H pluses to match the charge on the counterion in my acid. So we're going to name our acids following a set of rules that depends on the anion that you're looking at. So the first acid that we're going to be looking at is the binary acid. The binary acid matches H plus with some other nonmetal. And the state for this matters. So if the state is gaseous, the way that you name it is you write the word hydrogen and then plus. You don't write a plus, but write hydrogen space and then the name of the anion with "ide." So something like this would be hydrogen fluoride, not fluoride, I misspelled it. Fluoride, if it's a gas. Now, if it's aqueous, we do a different rule. So if I did HF as aqueous, we would do this. We would write hydro, and then all one word, whatever the stem of this is. So fluoride, the stem would be fluor. And then I write ic acid. Now, on the quizzes, I make an attempt to write what state it is. If the state is not written, assume that it is aqueous, because that is by far the more common state. It's very rare to be working with gaseous acid. It exists, but not common. One polyatomic ion follows this rule, because the rule, which your textbook doesn't say, unfortunately, the rule is actually, does the ion you're working with end in "ide"? And cyanide ends in "ide", so it follows this rule, hydrocyanic acid, for the aqueous state, or hydrogen cyanide if it was gaseous. So be mindful of HCN, because that's a common one that gets people tripped up. All right, that's the first rule for naming acids. So here's some examples of that. These two, we already did hydrogen fluoride, so these are done. But these two right here, this is a gas, so we would call it hydrogen bromide. If it's aqueous, we call it hydrobromic acid. All right. That's the first rule. The second and the third rules are based off of the end of your polyatomic ion. So does the polyatomic ion end in 8 or 8? If your polyatomic ion ends in 8, so for example, sulfate or nitrate or phosphate, then what you do is you strip off the 8 and you write ic acid on the end. If you have a polyatomic ion that ends in "ite", so hypochlorite or bromite or nitrite, these all end in "ite". We're going to strip off the "ite" on the end of the name and write us acid instead. Now, for two specific examples, and those are these right here. So I'm going to do sulfate and phosphate. I'm going to put a space here. What we do for these two is we get rid of the 8, but then we modify what's left so that it sounds a little bit better. So instead of having sulf, we do sulfur, and then we write ic acid or us acid. And then for phos, we do that. Again, that is just a spelling modification to make it sound better, but it is what is done. So be mindful that you don't write sulfic acid instead of sulfuric acid. So let's do some examples here. Give the name for this compound. This polyatomic ion right here is acetate. Acetate ends in 8, so we're going to get rid of that and then write ic acid for its name. So this is acetic acid. How about this one? What is this right here? This is nitrite. We get rid of the ite, and we add us to it. Acid. So this is nitrous acid. And then these two down here, we have to use the sulfur and the phosphor modified rules, so be mindful of that. This is sulfite. This is phosphate. So this would become sulfurous acid. And this would be phosphoric acid. Again, that should all be reviewed from Chem 140. All right, how much time do I have now? Just enough. Okay, so here's the acids page. I'll let you do this for 3 or 4 minutes. Type anything you get in the chat so I know where you're at. And then I will just write all the names on the board, and then we'll be done for the day. Okay? So I'll give you a few minutes to work. All right, we're almost out of time, so I got to go over the answers here. Excuse me. I can see answers popping up in the chat, though, so that's good. So this is perchlorate. So it becomes perchloric acid. BrO minus is hypobromite, so that becomes hypobromous acid. This is dichromate, which becomes dichromic acid. Oh, HCN, be careful. That's the weird one. And then this is phosphite, which becomes phosphorus acid. Be careful about this extra O in phosphorus acid. That extra O is not in the element phosphorus. So it does belong in the acid name, but if you're just writing the element out by itself, that O shouldn't be there. For sulfuric acid, we need to undo this change. So whenever you see ic acid, you should think, oh, okay, that's 8. So let me write sulfate. How many H pluses do I need? I need 2 of them. There you go. Nitric acid would be nitrate. Here's nitrate. How many H pluses do I need? I need 1 for this 1 minus. There it is. There's another 8. What is chromate? That's that. How many H's do I need? I need 2 to cancel that out. I see us acid, so I should think ite. Hypochlorite is that. So I get that as... I read it backwards. HClO. And then ic acid should be 8. Periodate is IO4 minus. That should be an I. There you go. And most of those look pretty good. All right, that's it for naming. I think the next section is, Lewis symbols. So yeah, that's where we're going to stop because we are right at the 7 o'clock line. So thanks for coming out to the lecture tonight. We're going to keep whipping through chapter 4. The next section starts with a little bit of review, and then we're going to do some new stuff as we draw bigger Lewis structures than we did in 140. So look forward to that tomorrow. Make sure that you get that lab worksheet in tonight. It is due. Tonight is last call. The last call announcement will be going out right after I shut down the video. So yeah. And then work on quiz number 3, which is due next week. See you tomorrow.